My name is Kaoru Mizuta from the University of Tokyo. Today, I'd like to talk about our recent results on substantial efficiency of trotterization for low energy states. So this work is a joint work with Tomotaka Kuwahara in RIKEN, and this is also available in this archive. So this is the outline of my talk. So before moving to the main results for low energy states, I briefly introduce the Hamiltonian simulation and trotterization. So in this talk, I mainly focus on Hamiltonian simulation. So in this problem, we wish to solve the Schrödinger equation by quantum computers. So namely, for a given initial set psi, we apply a set of unitary gates, and we wish to realize exact time evolution state with a designated accuracy if shown. So in this task, we can expect the exponential speed up by quantum computers, and quantum dynamics computed by the Hamiltonian simulation has vast applications in condensed matter physics and quantum chemistry. So Hamiltonian simulation is one of the largest problems in quantum computation. In this field, one of the ultimate goals is to construct fastest algorithms with guaranteed accuracy. Namely, we wish to achieve theoretically best scaling in the system size n, evolution time t, and the allowable accuracy if shown. So in the past several decades, there have been proposed many algorithms proposed. So for example, trotterization is one of the most famous algorithms. And recently, linear combination of integers or quantum singular balance transform have been important, which are known as post-trotter algorithms. Here, I focus on the trotterization, or often called product formulas. So in this algorithm, we split the Hamiltonian into several terms, and we construct approximate time evolution operator by the time evolution operators under each term for small time tau. So the second, this formula represents the approximate product formula for the order P product, order P cases. And maybe many of you are already familiar with Lee-Suzuki-Trotter formula for the first order cases and the second order cases. So in order to run the algorithm for large evolution time t, so we split into R parts, and we repeat the application of the product formula for the time t over R. So namely, the complexity R, or often called the Trotter number, is determined by this splitment. So in order to achieve the desirable accuracy epsilon, so we determine the number R so that the accumulated error in the R steps becomes smaller than the allowable error epsilon. So namely, the error of trotterization is an important factor which determines the computational complexity in trotterization. So let me introduce the error of trotterization. In trotterization, we often consider the worst case error for all the possible initial states, so like the right-hand side. And this is equal to the operator norm between the exact time evolution operator and the product formula. Naively speaking, so the product formula is obtained by the Taylor series expansion in the small time tau. And this also gives the error bound. So this is a bound called one norm scaling. And this is typically large polynomially in the system size n. However, this scaling is not optimal one. So actually, recently, the error bound with commutator scaling has been revealed in general product formulas. So this error bound states that the Trotter error is bounded by the summation of nested commutators. And this properly reflects the property of trotterization in that the Trotter error becomes exactly 0 when all the terms commute with one another. Importantly, for generic local Hamiltonians, many terms in nested commutators vanish because, for example, when we consider commutators between distant local interactions, so they become exactly 0. And by using the property of local Hamiltonians, the error bound with commutator scaling is proportional to the system size n. So based on this commutator scaling error, we can determine the complexity of trotterization. So by solving this inequality, so we can determine the Trotter number in this form. So importantly, so this Trotter number is available for all the initial states because we use the worst case error. And importantly, by calculating the gate counts by this Trotter number and the number of gates per each product formula, so we can achieve better system size dependency than the post-Trotter algorithm. So now, the trotterization is one of the most promising algorithms in future fault-tolerant quantum computers. So next, I would like to discuss our recent results on low energy states. So is there any remaining problem around trotterization? Maybe one of them is the usage of worst case error. So although the worst case error is available for all the initial states, but we do not need to consider all the initial states in practice. So we are often interested in some specific class of initial states, and the worst case error overestimates the error and cost for specific initial states. So one important question in this direction is whether or not we can improve errors and costs for physically motivated classes on initial states in practice. Recently, for example, how random initial states or highly entangled initial states can improve the error and cost quadratically in the system size n. Another interesting example is the low energy initial state, which I will focus in this talk. In the past 5 years, several studies have revealed that the error and cost can be improved in the initial state energy. And among these studies, our result is the best result so far with achieving the theoretically best scaling in the initial state energy. So let me discuss the detail of our result. First, I specify the setup. Here, we consider generic n-qubit local Hamiltonians with positive definite terms. Here, we define 2 important values. The first one is the extensiveness, G, which is defined by this formula. So this is we consider the summation of the norm of the Hamiltonian each term hx acting on a certain site I, and we take the maximum for all the sites. So this means maximal energy scale per site. And in this talk, I mainly focus on the Hamiltonians with finite range interactions. And in that case, the extensiveness G is a size-independent constant. The second value is the energy scale of the whole system, so defined by n times G. So this becomes an upper bound of the norm of the Hamiltonian. So with using these 2 values, we define the low energy states completely closed in the low energy subspace. Namely, we consider initial states which is written by the superposition of energy eigenstates whose energy eigenvalue En is smaller than a certain value delta. And we mean the low energy by the fact that the initial state energy delta is much smaller than the orbital maximum energy scale of the whole system, Ng. So we can define the errors for low energy initial states by the worst case error for low energy initial states. So in order to compute by the operator norm, so we insert the projection to the low energy subspace. The important question in this direction is that whether or not we can improve the trotter error for low energy states compared to the one for orbital initial state cases. So as I introduced in the introduction part, the error bound for orbital initial states is given by the commutator scaling, and it is proportional to the system size n. And importantly, so it is also proportional to the energy of the whole system, Ng. So in our study, we obtained the improved error bound for low energy initial states. So this is an inequality obtained for low energy initial states. So by replacing the Ng in the orbital state cases by the initial state energy delta, we obtain the error bound for low energy states. So and states. Importantly, the blue part, the second term, is which is logarithmic in the system size, represents the leakage from the low energy subspace. So this is here. So importantly, so our scaling is exponentially better than the orbital state cases in the system size n. As you can see, the second term, the leakage is usually negligible, and as you can see, so the error bound decreases in the broad low energy regime, where the initial state energy is smaller than the whole system energy, Ng. So let us compare our results with the previous low energy results. So in our bound, in our results, the bound is proportional to the initial state energy and logarithmic in the system size n. And these are the previous low energy results. So in their bounds, so they obtain the scaling polynomially large in the initial state energy and also polynomial large in system size n. So we have achieved the polynomial improvement in the initial state energy and exponential improvement in the initial system size n. So I'd like to mention about the derivation, so which is the origin of our improvement. Our achievement is that we obtained the error band reflecting both low energy property and the commutator scaling. So as I mentioned in the introduction, the Trotter error can be represented by the nested commutators, and for low energy initial states, so the nested commutators in the low energy space appears. And we show that this is bounded, this increases at most linear in the initial state energy. So this is polynomial improvement from the previous low energy results. The second our contribution is a leakage based on the nested commutators. In our studies and the previous low energy studies, so we use a Hastings theorem on leakage. So this theorem states that the leakage from the low energy subspace to the high energy subspace by the local operator is exponentially suppressed. With using these theories, so we show that the leakage by the Trotter error is approximately bounded by the leakage caused by nested commutators, which is a local operator. So this is in contrast to the previous studies in which the leakage by the Trotter error is determined by the leakage by the product formula, so which is a non-local operator. So this is the origin of exponential improvement in the system size n. So let me compare the complexity obtained by the error for low energy states. So in our study, we obtained the complexity in the form of this equation. And as you can see, so by replacing the energy by the initial state energy delta, we obtained the complexity in this form. And so in our results, we show that the speed up in the broadest low energy regime, where the delta is smaller than the energy, takes place. And we also show that the system size dependency is exponentially improved. So this is in contrast to the previous low energy results. So in the previous studies, they obtained the complexity in these forms. And in the previous results, the speed up for low energy initial states takes place only in the narrow regime, where the initial state energy is smaller than the n to 1 over p plus 1 times g. And they also obtained the worse or cross scaling to the case for orbital initial state cases. So finally, I would like to discuss about the extension to other low energy initial states. So so far, we consider the initial states completely closed in the low energy subspace. However, so it is not easy to prepare or confirm such low energy initial states in general. So in order to overcome such a difficulty, we consider extension to weakly correlated initial states with small expectation value. So namely, we consider product state or something with satisfying the condition on the expectation value of the Hamiltonian. Importantly, so such a state is not necessarily closed in the low energy subspace. For such low energy initial states, we proved the improved error bound and the Trotter number R in these forms. So in contrast to the previous section, so the error bound and the Trotter number includes a square root n here. So this comes from the concentration bound I used for the proof. So this states that the weakly correlated initial state is approximately closed in the low energy subspace, whose energy is the expectation value plus a square root n times g. Anyway, so by using these results, we can show that the speed up to the the quadratic improvement in the system size n can take place for the low energy regime, where the energy expectation value is smaller than the whole system energy. So this is a summary of my talk. So we show that the trotterization can be substantially efficient for the broad low energy regime, where the initial state energy is smaller than the whole system energy. And finally, I would like to emphasize the optimality of our results. So we emphasize that our results have achieved optimal scaling in the initial state energy because so it has been shown that the Trotterization for arbitrary states in the generic product formula is at least linear in the system size n, and our error bound should reproduce this optimality when we set the initial state energy delta at n times g. So the error linear in the initial state energy is optimal. So as a future direction, so there are many variants of trotter-based algorithms. So we expected that the advantage of the low energy states can be extended to various quantum algorithms in the future. So and that's all of my talk. So thank you for your kind attention.
Thank you, Kaoru. Let's take a question here.
So can you give an intuition on which high energy state leads to a large trotter error?
Actually, so there's no. Actually, I only proved the upper bound. So it is. So it means that the high energy states always. So it does not mean that high energy states always gives a higher trotter error. So that's it.
So got a question. There's other properties of low energy states you might be able to take advantage of. So for example, if we promised that your system obeyed an area law, and you're looking at, say, k-local Hamiltonians, have you considered how the trotter error would end up behaving in that case as well?
Actually, we do not consider about some specific properties like area law or about the low energy state. So because of we only use actually in the proof we only use the property of this equality. So we do not consider area law or something in our proof. So actually, the locality and the low energy property is sufficient. Yeah.
That's the question here.
Thanks for analysis talk. In your extensions, may you comment applicability or extensions of this to, say, Gibbs states where you have a super mixture of eigenstates, but you don't have a limited cup?
Actually, in our formalism, Gibbs state is essential. So we cannot consider Gibbs state because we have in general we have leakage from the low energy subspace, and so in order to extend our result to Gibbs state, so we have to estimate how large leakage from the low energy subspace is existing. So actually, this is left for future work.
But square root of n result which you showed.
Actually, so this is not for Gibbs state, like a product. Sorry. This is just for product state or low entangled state. So actually, if the Gibbs state is low entangled, I expect that our result can be upright.
If delta is a finite energy density, so it's proportional to n, do your results kind of go away?
Yes, that's right. But we show that. So actually, there is a constant region. So when the initial state energy delta is smaller than some constant times whole system energy, then we can expect a constant speed up. Yeah.
No, let's thank Kaoru again